All right, so again, we'll just wait 1 more minute before we continue our discussion. So while waiting, anyone who has a question so far or clarification? All right, so it's already 12:56, so let us continue now our discussion. But before that, let me just check if you guys are already ready. So just give me a thumbs up just to let me know that you guys are already ready. Okay, 1, 2, 3, 4, 5, 6, 7, 7, 8, 8 out of 13. All right. So anyway, the other will just catch up to us. Okay, so that's it for the voltage drop, okay, across this R1 and R2. So R1 and R2 is 12 volts, R3 is 9 volts, and then for the R4, R5, and R6, it's 27 volts. Okay, so again, if you're wondering on why they are equal with each other, just go back to the rule wherein E total or the E1 is equal to E2 or equal to E3 also at the same time. Okay, with this one with the 3 resistance. So yeah, that's it for the parallel connection. The next one, letter D. Letter D is the current through each resistor. So this is now only super easy since we already have the individual voltages and then the individual resistances. So in here, for us to be able to get the IR1, all you have to do is get the V1 divided by ups. IR1 is equal to V divided, yeah, V1 divided by I1. Ah, IR1, I is equal to V, my bad. V1 divided by R1. Okay, so that's it for the IR1. So the formula for that one, I1 is equal to V1 divided by R1. Okay, so if it's I total, then it should be V total also divided by R total. But since we're only getting the individual currents, then you should also have the individual voltages and then the individual resistance. Okay, so again, let's just base it right here. Oops. And then base your voltages right here for the V1, V2, V3, V4 up to V6. Oops. So for the V1, we have 12 volts, which is coming from this one right here. So divided by the R1, which is 6 ohms. So 12 divided by 6 is 2 amps. So that's the current that's flowing on the IR1. Okay. For the R2, so 12 divided by 12, okay, which is equal to 1 amp. IR3 is 9 divided by 3. Okay. So all you need to do is get the individual voltages that is coming from your answer right here. So again, if you have an incorrect answer when it comes to individual voltages for the let's say ER2, ER3, ER4, then you will also arrive on a incorrect answer for the individual currents. So make sure that everything that you are solving is correct because it will affect your entire solution. Thus, you will get an entire incorrect answer at the same time. Okay, so just get the V1. So for the IR4, IR5, IR6, so they are the same for the R4, R5, and 6, which is 27 volts, and then divided by their individual resistance, which is R4 is 15, R5 is 90, and then R6 is 30. And then just do the math, and then you will get those individual currents. Okay, and then for the power, so for now, we haven't discussed the power yet, but the formula for the power is equal to this one. P is equal to E times I, or P is equal to V times I, since E is equal to V. So they are just the same. Okay. Or if voltage is not available, then you can use current also. However, it should be I squared times R. Okay. So in here, let's say, yeah. So instead of voltage, then you have to use now the R, but you have to square the I. So later on, we're going to have a derivation on why we have I squared times R. The same with this one. Let's say you don't have the current is not available, then you can use E squared divided by R. So later on, we're going to have a derivation also on why we have this one, why we have this formula right here, and so on and so forth. So, any of those formula, you can use any of those, you will arrive at the same result, which is 144 watts. Okay. So you can verify this one using your calculator. So you can use this one if they are available, and then you can use this one if they are also available. Okay. So that's it for the example number 3. So are we clear so far? Hello. What about the others? All right. So 1, 2, 3, 4. So at least there are now more respondents than before, because before there's only one. There's only Mr. Donato. Okay, so 4 out of 13 participants. So I hope the other were also able to follow. So that's it for the example number 3. Then let's now move on to your first exercise, which of course you're going to answer this one on the canvas. So of course, we already have a similar example for this one. So a series connection, we have R1 and R2. Just calculate the ohmic value of R2. Okay, it's just that there's an additional one resistance. So before we only have two resistance, but right now we now have three resistance, and then one unknown, which is the R2. Okay, so just answer this one later on after our discussion. And then one more exercise that you need to answer is this exercise number 2, to be answered in Canvas again. So this one is quite similar with example number 3. So if you were able to follow and get this one, this example number 3, then you won't be having a problem to answer this exercise number 2. Okay, so we have here the given values, and then the questions: calculate the total equivalent resistance, total current, voltage drop across each section, the current through each resistor. So just take note that the one that is being asked in here is the voltage drop across each section. Okay, not each resistance. So what are those sections? So we only have 3 sections. So this is your first section. It's composed of R1 and R2. And then we have here the second section. It's composed of the R3. And then we have here the third section, which is composed of R4, R5, and R6. Okay? So just take note on this one, letter C. And then the current through each resistor. Okay, so it's not each section, but it is now each resistor. Okay, so we should, or you should have 6 individual currents. So I1, I2, I3, I4, I5, I6. Okay, and then the total power taken by the entire circuit. Okay, so just use this formula right here. So P total is equal to E total times I total. So if you're solving for the total, then you should also have the other total values. If it's individual values, then you should have the other individual values. All right. So are we clear so far regarding with exercise number 2? What about the others? There's only one who was able to follow. So there's three out of 13. So I hope the others are listening so that just in case that you guys have a question, so you can ask it now. Anyway, so that's it for the exercise number 1 and 2. So there's more later on. But before that, let's talk about electric power. So electric power or power is the rate at which work is done. Okay. And in the mechanical system is generally expressed in horsepower, okay, or HP. So it is equivalent to the rate of 33,000 foot-pounds of work per minute. So later on, we'll have the computation on why it's 33,000. Okay, so in here, here's a representation of horsepower. So that is the power of this horse, which is just, let's just say that one. So it's equal to 33,000 foot-pounds per minute. Okay, so this was discovered by James Watt, at the year 1782, because they found it necessary to specify how much power his new steam engines would develop in terms of the horse push a crank as they walk in a 24 feet diameter circle. So he experimented this one using a horse, let's say an average horse, not so young, not so old. So that horse is pulling a where is it one pulling a crank, okay, for in 24 feet diameter circle. So with that experiment he found out that 1 horsepower is equal to 33,000 foot-pounds per minute. Okay, so more explanation on how did we get this 33,000 right here. So of course, uh, that one is depending on the diameter or the circle that's being circulated by that specific horse. So since the average horse was assumed to exert a force of about 175 pounds, so this is the one that he had used. Okay, so he let that horse to push, I mean, pull, okay, 175 pounds and made 2.5 complete revolutions per minute. So it followed that 1 HP was equivalent to 175 times 24 times 5 times 2.5. Okay, so with this computation right here, he arrived at 33,000 foot-pounds. So in one uh, revolution or 2.5 complete revolution per minute, okay, which is now equal to 1 HP. So that's equal to 33,000 foot-pounds per minute. Okay. So if you're still confused on how did we get this 33,000 foot-pounds, so you know, don't sweat in looking for uh, the values on why we arrive at 33,000, because the one that he had used is 24 feet diameter circle. So that depends on what you're going to use. So it could be 16,000 if it's 12 foot diameter. So it's just that he's the one who come up with this kind of value. Okay, so just stick with the 33,000. You don't need to learn more. Why is it 24? Why is it not 20? Why is it not 18? Why is it not 30? And so on and so forth. Because of course you will arrive at a different answer with this one right here. Well, later on, when the unit of electrical power was adopted, so it was designated the watt in honor of the inventor James Watt. Okay, so with this invention, so the unit now is equal to watt. So that is why 1 horsepower is equal to 1 watt. So those two are just the same. So 1 HP is equal to 1 watt, right? And then here's the formula for the power. So of course, when it comes to mechanical, okay, right here, mechanical system. So we need to use if power and then a current, okay. So in here, they've arrived that let's just say that 1 power is equal to 1 watt, okay, or the more derivation of this one came from 1 joule per second, okay. So when we see again power, it's the rate at which work is done, okay. And when we see work, it should have a or let's just say in terms of mechanical, okay, because you cannot make that mechanical work if it doesn't have an electricity. But of course when it comes to horse, it doesn't need an electricity and a current because it has its own energy to do a certain power. But when it comes to mechanical, So you should have electricity and then a current. So that is why we have E times I for us to be able to get the power. So the rate at which electrical energy is transferred to a circuit. So the time rate of doing work, the unit of electrical power is defined in terms of joule per second, and the latter being the work done when 1 coulomb of electricity is moved through a potential difference of 1 volt in 1 second. Okay, so to make it simple, in our houses, of course, we're talking about watts, okay, or this one right here, wattage or kilowatt hour when it comes to our bills in Beneco or Meralco. So let's just say that if we have 10 LEDs, that's one, or this one will accumulate a power of 70 watts. Okay, so let's just say that 7 watts per bulb since there's 10. Okay, the same with this one. So we have 10 eco bulbs, a total of 180 watts. So 18 watts per eco bulb since we have 10. And so on and so forth. So of course, the larger the appliances, the more wattage that it will uh, accommodate or it will use. Like refrigerator is 3,500, hair dryer is 1,200, and so on and so forth. So just imagine that, let's just say that your E is the voltage that appliances will need, and then the current that that device will need. Okay, so of course, the larger the device, the more current that it will need. The larger the device, the more voltage that it will need. Okay, so sometimes it needs 50 volts, 100 volts, and then depending on the current also. So with that, you'll be able to get the value of the wattage that is being used by that specific device. All right. So are you guys able to follow so far when it comes to the concept of power? Hello, hello, hello. So if you want to study more when it comes to power, though, when it comes to power, all you need to memorize is this one. Okay. So you don't need to, memorize 33,000, this 175, etc., etc. So when it comes to power, just know this formula. No, this is just a short history on how did they invented the calculation when it comes to power. Okay, so P is equal to E times I. So if you want more explanations, then you can visit. Just go to modules. You can visit this one, this one electrical power. So there's three parts for this one. So explaining the wattage, uh, how did they come up with that power, one watt is equal to one power, etc., etc. So it has three parts. So second one is an example problems. The third one is calculating the cost of electric power. Okay, so yeah, this will explain to you guys on why do we have such thing. All right, so that's it for the power. So knowing that we have P is equal to E times I, so this is now where the derivation on why we have the other formulas. Okay, so as we all know, E is equal to uh, V is equal to I times R. Okay, so this E right here is the same with V. So V is equal to I times R. Okay, so where this one came from? So this one came from I is equal to V divided by R. Okay, so you can also get the value of R, wherein R is equal to V divided by I. Okay, so with that being said, so you can actually replace this letter E right here, okay, by I times R. So you will arrive with this kind of formula. So IR times I. So if you're going to simplify this one a little bit more, so this one will become I squared times R. So that's how we've come up with this I squared times R right here. Oops. I squared times R. Okay. So are we clear so far? Are you guys able to get that one? So just let me know if you guys cannot follow. So we can go back to that part again and then explain more, maybe give more example, give more definition maybe. Okay. All right, so that's it for the I squared times R. But what about E squared divided by R? So the same concept. So in here, if we don't have, let's say, I, okay, so you can replace this I right here using this formula. I is equal to V divided by R, okay, wherein V is the same with E, so I'll just put here E for consistency, divided by R. Okay, so if we're going to simplify this one a little bit more, so this one will become E squared divided by R. So that's how we've got this E squared divided by R right here. Okay, so are we clear so far? All right, so let's now talk about horsepower. Okay, so when it comes to horsepower, we're in this HP right here, it's being now converted into mechanical power. So it's not literally the horse. Okay, it's just based from the horse, but the one that is now working is the mechanical power. So it could be any mechanical system. Okay, so in here, they were able to find out that 1 HP is equal to 746 watts. Okay, wherein sometimes we say that 1 HP is 3/4 of kilowatt. So from the word kilo, okay, so it's being multiplied to 1,000, and then as you guys may all know, it's 746, so they just approximately said that it's 3/4 of kilowatts. Okay, so that is why 1 HP is equal to 3/4 kilowatt. But in some cases, you're saying that 1,000 watts is like the same with 1 horsepower, but that's not actually true. It's just the way for us to make the computation easier. But the exact one, okay, is 746. So sometimes they also use 750 because it's 3/4 okay, of kilowatts. But if you want to get the exact computation when it comes to wattage, it should be 746. Okay. So let's have an example for you guys to get the application of this one. So a building load consists of 30 100 watt. So this building has a 100, I mean 30 100 watt bulbs. So this is just a uh, let's see, a similar picture. Okay, just to give you guys an idea. So 30 100 watts, and then 50 75 watts, and then 40 60 watts incandescent lamps. So we have three different lamps. Okay, wherein one is consuming 100 watt, another one is consuming 75 watts, another one is consuming 60 watts. Okay, so all connected in parallel to a 116 voltage source. So knowing that they are connected in parallel, so we only have one voltage value when it comes to individual uh, lamps. So the question here is calculate the total power. So for us to be able to get the total power, we should get the total power that's being accumulated by this 30 100 watt. So that's super easy. All you need to do is multiply this 1 by 30. So this, this bulb 100 watt, just multiply to 30, you will get 3,000 watts. Okay, that's the entire 100 watt. And then for the 75 watts, it has 50 individual lumps. So just multiply that one to 75. 50 times 75, you will get 3,750. Okay. Then the same with 60 watt. Okay. So multiply that one by 40. You will get 2,400 watts. Then once you're done with that, then all you need to do is add those wattage. Okay. So 3,000 plus 3,750 plus 2,400, and you will get a total of 9,150 watts. Okay, so letter A now is being answered, or has now an answer, which is 9,150. So for the letter B, the total current, okay, so for you to be able to get the I total, you should have, yeah, you can use this formula, okay? So I is now equal to P divided by I. Yeah, that's correct. P divided by E, not I, because I is the one that we are solving. So P is 9,150, which is the total power. And then 116 is the uh, total voltage. Okay, so you will get 78.9 amps. And then for the current through each lamp, so all you need to do is get the individual uh, wattage, okay, of this one, since it's being asked the individual current through each lamp. So in here, just get the total power of that one. Let's say that P100, 3,000 divided by 30, since you're getting the individual 100. Okay, so you will get actually 100 watts in here. Okay, and then you will get uh, 75 watts in here, since that's the individual value. This one just made the solution longer. Anyway, 2,400 divided by 40, you will get 60. Okay, so just divided by 116, since that is the voltages that is flowing on that uh, bulb or lamp. So with that, you will get 0.863, 0.646, and then 0.518. So uh, those are the currents that is flowing on each of those resistors. So are we clear so far? So I'll give you guys 1 minute to analyze this one, 1 or 2 minutes. And if you have a question, just let me know. And once you're done, just give me a thumbs up. So just to let me know that you were already able to understand this example right here. Okay. So again, maybe you guys are wondering why we only have one individual voltage right here, because they are again connected in parallel. So whatever is your E total, it's the same with E1, E2, E3, E4, and so on and so forth. The only time that you will get, let's say, a different value when it comes to voltages is if it's in a series connection. Okay, but if it's in parallel, then those are just the same. So E total is equal to that path, second path, and then third path. Right, so we now only have 5 minutes left. So I think we still need one more meeting. So we'll be having a part 4 for this one, just to finish the module 1 and 2. All right, so that's it for the example number 3. So just in case that you still cannot understand this one after the meeting, so just message me again. Okay, so just ask a specific question, then I'll try to answer your concern regarding with this given examples, wherein for you it's not that clear. So let's now move on to the example number 4. So using the data from example number 3, so the same given values, calculate the given equivalent resistance of the entire load. So if you want to get the R total, then you can use this formula, or you can use this formula right here, okay, wherein R is equal to E squared divided by P. But any of those formula will be fine, okay, as long as you have the correct values. So you can use E divided by IT, okay, so you will get 1.47 ohms, or you can use this one, P divided by I squared, okay, which this one came from this formula right here, wherein you will get the same result, 1.47 ohms. So just verify this one later on, okay, so you can use any of those formula, then it will give you the same result, okay. And then for the individual resistances, then all you need to do is get the individual currents also, and then the individual voltages. But since I mentioned that they are in parallel connection, then you only have one value when it comes to voltage, which is 116. So the formula for resistance is again R is equal to V divided by I. So if you're getting individual resistance, let's say R1, then you should get the V1 and then I2. I1. Okay, wherein in here we have V1 divided by I1. So this 0.863, 0.646, 0.518, this one came from our previous results. Okay, so again, if you have an incorrect answer when it comes to this those individual currents, then you will also get an incorrect answer for those individual resistances. So just be careful when it comes to solving, when especially the individual uh, values for the resistance or currents. The same with the voltages. Okay, so just use your calculator, and then you will get those individual resistances. All right. So again, I'll give you guys a minute to analyze this one, example number 4, and then just give me a thumbs up once you're done and you are able to understand this one already. Okay, Mr. Donato already got it. What about the others? So let me just check if you guys are really in front of your computer or smartphone. Mr. Paran, no response. So I guess he's not around. Miss Rona, yan. So kaka-respond lang. Miss Rona. Okay, Miss Leah is already there. Yes, Miss Rona is not around. Mr. S. Talilia, Mr. Nathaniel.
Dito po, sir.
Okay, Mr. Francis,
Dito po.
Mr. Aaron, Miss Daniela. Okay, so I think sumagot si Mr. Aaron pero hindi ko narinig. Anyway, Miss Maris, Mr. Mark. Okay, Miss Daniela is around. Mr. Mark, Miss Sophia. Alright. So, dalawa yung wala.
Here, sir.
Okay. Alright, so again, we don't have enough time anymore, so we now only have 1 minute left. So there's still 12 slides remaining. So we'll be extending our meeting. So just wait for the part 4 since we need to finish this module today. Okay, so goodbye for now, and then see you guys later on the part 4.